going to do is start with the October 20th test 2. October 20th of last year. Once again, just general reminders. Tomorrow morning, 10 a.m. in here. Bring pens, pencils, erasers, whatever you need to write with. Highlighters, markers, all that kind of fun stuff. If you want to bring a ruler, that's okay. And a calculator. No notes, no books, all that stuff. Probably what I'll do is just copy these equations onto the new test for tomorrow, and we start with the multiple choice. So which one is Hooke's law in vector notation? B. What are the units of the coefficient of friction? C. Block is resting on a table, you push down on it, the normal force, A, increases. Circle with the cross is a vector doing what? Pointing into the page. Atwood's machine has friction, it has friction. What is the ratio of E start over E end? Greater than 1. Momentum is the product of what two quantities? Mass and, you said volume?
Velocity.
Okay. You said it with confidence, but it's velocity. Thread is being pulled off a spool. The spool revolves at a constant rate. Which of the following is false? C. True or false in this situation is d omega dt non-zero. It is 0. D omega dt is the change in omega, and I said that omega is constant, so it has to be false. Atwood's machine has no friction. Yay, no friction. What is the ratio of E start over E end? 1. Circle rotates 3 times in 6 seconds. What is the period? D. Object in translational equilibrium means what? Oh my goodness. The answer has been stated correctly, but since everyone in the room has said A, B, C, and D, can we narrow it down a bit? It's C, translational equilibrium. A is what? Conservation of linear momentum. B is what? Angular momentum, conservation. D is what? Rotational equilibrium, yes. Which represents the unit of work? Newton meter. What is another way of saying Newton meter in one word? Joule. Excellent. We've gone over 12. Which one is rotational equilibrium? B. Circle of radius r has what circumference? 2 pi r for circumference. Huh? Circumference is 2 pi r. We have a disagreement? No. Okay, I just thought I heard pi r repeatedly, and I'm like, whoa, we need to have a talk. Normal force is always blank to friction force. What is blank? Perpendicular. Quick question. Vectors going in the same direction are what? Vectors going in opposite directions are what? Anti-parallel. Okay. Rotational mass is, sure. Unit for frequency is inverse seconds. What's another way of saying inverse second? Hertz. Real quick, spell hertz. Yes. Rocket spins a disk from rest. Which value is constant? D, alpha. Elastic collisions conserve momentum and energy. Yes?
Can you explain why 17 is D?
Okay, if it spins from rest, I will clarify that the rocket, the force coming off the rocket is constant. So it's always putting out X number of newtons. So if it's producing X number of newtons, the sum of the torques, which is the force times that radius, is the moment of inertia times alpha. Or alpha is Fr over I. Radius doesn't change, the moment of inertia doesn't change, the force of the rocket doesn't change, so alpha doesn't change. It's constant. Yes?
So if 18 if that was inelastic, would it be just momentum?
Elastic collisions conserve energy and momentum.
So even my TA is like, well, inelastic conserves total energy.
Well, the thing that we have to have, they're being picky. In all collisions, in the truest sense of the word, energy, as in energy of the universe, it is conserved. The energy that we specify in this class is mechanical energy. And the way that they say it is, in the lab, is energy is conserved, yes, but you can't quantify how much energy is going into various things such as sound, heat, all that stuff. The way that I interpret energy is mechanical energy, energy that you can watch and predict and quantify and label. And so we're using the same word for two different things. So in the experiment yesterday, our energy is their mechanical energy. Our energy of the universe is their energy. And granted, I'm the professor, so I should be able to tell them, but the one thing that they've yet to do is they need to change the name of the lab to conservation of momentum and mechanical energy. That's the truest sense of that lab. And I only got 6 weeks here, so I'm not making a big deal of it. But in my tests, it is energy and momentum for an elastic. Inelastic, and this is the big difference, in an inelastic collision, you can say, yes, energy final is equal to energy initial. But you can't go beyond that, because energy initial gets distributed into energy of heat, energy of sound, energy of changing the shapes of the object, and you have no way of determining those numbers. So the energy that we are concerned ourselves with, energy for an inelastic collision, it's not conserved, it's not quantifiable. We can't just write down numbers. So if you can't write down numbers, then it's not really conserved in a constructive manner. On a rotating disk, radial acceleration does what? B. Whoa. You said B with confidence, but you're wrong. What is it? Someone said it. A. Like that.
Can you explain that?
When initially the velocity on a point, in this particular case, since it's rotating counterclockwise, the velocity at that particular point is due left. A little bit later, when it's here, it's due south. So this velocity vector changed. How do you get that velocity vector to change? It must have an acceleration. This acceleration is always pointed inwards. So it's when it goes from there, like that vector and that vector produce that vector, which points inward, and so on until you end up with that. And so it's just a gradual change in vectors. You are running around the circle. You run faster. What doesn't change? All right. When you run faster, what happens? Your velocity increases. So if your velocity increases, does your frequency increase? So if you run faster, you're running around more times, so the frequency does increase. The period does what? It decreases because it takes less time to run around the circle. Does your kinetic energy increase or decrease? It increases if your velocity increases. Angular momentum. Angular momentum is I times omega. Now, I doesn't change, and that's the answer, your moment of inertia. But your rotation increases, which changes your angular momentum. Work has what units? Joule. Units of radial acceleration are what? Meters per second squared. This is the units of what? C is the units of what? Blank over inverse seconds is what? Wrong, but appreciate it. Angular velocity has the units of what? Inverse seconds. So inverse seconds squared is angular acceleration. Or alpha. Second is the unit for what? Period. Circle rotates 8 times in 4 seconds. What is the frequency? 2 hertz. Circle dot is a vector. Out of the page. Excellent. All right, right-hand rule game. F cross A. C. D cross C. E. A cross C. F. C cross D. F. B cross A. F. There we go. So C, E, F, F. There was one time, well, I usually get, sometimes I get 3 out of 5 to be the same letter, like on a multiple choice. One time in a multiple choice test, it was just random, but it was 10 C's in a row. And so some people by the 8th or 9th C started hitting other answers because they just couldn't believe that the run would go that long. All right. Problems. All right, in this particular case, we've got a disc, a bar, a stick is welded onto the disc of L is twice that of the radius. We know the mass of the disc and the stick. I want to know the radius R if from rest it rotates 50 times in 20 times the square root of pi seconds. Now, when you see something like this, you go, time is 20 times the square root of pi? Seriously? Yes, seriously. Maybe Dr. Eschenberg was desperately trying to make the numbers work so that you would end up with a whole number at the end. So maybe we should just watch and see what happens. It's a rotation problem. It's a rotation problem where alpha isn't 0. In this case, alpha is most definitely non-zero. In this particular case, you need to write that theta is theta naught, which is 0, plus omega naught t, which is 0, plus 1/2 alpha t squared. Since I give you the number of rotations, you have to know that theta is 2 pi n. So 2 pi n is equal to 1/2 alpha t squared. So we need that equation. I have time. I have number of rotations. I don't have alpha. Well, the sum of the torques is equal to I alpha. There's only one force producing one torque. So this is Fr equals I alpha. Or alpha is Fr over I. Substituting that into here, 2 pi n is 1/2 Fr over I t squared. We know everything but the moment of inertia. Well, actually, we don't know what R is, and we don't know what the moment of inertia is. But we do know one thing, that the bar is directly across the circle. So I of the stick plus I of the disc. Because the disc and the stick are both rotating around their centers of mass, it is unnecessary to use the parallel axis theorem. So the moment of inertia is 1/12 m stick L squared plus 1/2 m disc R squared. And answer, yes, you will be given, for a second there I was like, what am I saying? You will be given the basic moments of inertia, stick, point, and disc. That's all we're going to play with in the test. So know stick, point, and disc, and know how to use the parallel axis theorem on the stick and the disc. In this case, L is 2R. So this makes it I equals 1/12 ms 4R squared. L is 2R, L squared is 4R squared plus 1/2 mdr squared. This leaves me with 1/3 ms R squared plus 1/2 m disc R squared. Factor out the R. I equals R squared ms over 3 plus md over 2. And that's the moment of inertia. Plugging that into here, 2 pi n 1/2 FRT squared over R squared ms over 3 md over 2. I'm looking for the radius. That's the only quantity I'm looking for. I know N, F, T, ms, and md. Solve for R. That R cancels with that R. I'm going to bring that R up and the 2 pi n down, and I'm left with R equals ft squared over 4 pi n ms md, and there I go. Now plugging everything in, F is 140. Time squared is 400 pi. Time squared, or the square of 20 squared, is 400. Square root of pi is pi. And so I get this over 4 pi in 50 ms is 20. Mass of the disk is 120 over 2. So one of the reasons why T had a factor of pi in it, pi cancels with this. 50 times 4 is 200. 400 divided by 200 is 2. So it's 280 divided by whatever that is. And I get a radius of 4.2 meters exact. So if you see a 20 times the square root of pi or something where the time is just freakish, like some weird fraction, you know I've been cooking the numbers to work out well. And so that's the answer. So you had to use this, manipulate moment of inertia, plug it all in, and then there you go. And that's number 1. Number 2. Number 2, standard Atwood's machine with energy. When I meant by M1 is question mark, I wasn't asking for M1. I'm just saying that M1 is an unknown. I'm looking for mu sub k, that is in the box, and I'm looking for the fraction of energy remaining, or EF over EI. In its initial state, it's not moving. So there is only potential energy, which is M2GL. That's its initial potential energy. Its final kinetic energy has no potential energy. So this is 1/2 M1 plus M2 V squared. V final was given, that's V. L is given. The ratio of M2 and M1 are given. All I have to do is find mu sub k. Now, M1 feels a friction force in that direction and a normal force in that direction. The sum of the forces in y is equal to 0, which is equal to Fn minus M1g. So Fn is equal to M1g. Friction force is mu sub k Fn, which is mu sub k M1g. So the work removed, force times distance, is mu sub k M1GL. If block 2 fell distance L, block 1 slid distance L. So now that we have our basic states and the energy released during, let's put it all together. The potential energy initial minus the work is equal to the final kinetic energy. This gives us with M2G capital L minus mu sub k M1 GL equals 1/2 M1 plus M2 V squared. It has the classic substitution solution in it, which means I did not give you the specific masses, nor did I ask for them. But what I did give you is a ratio. M2 is 4 M1 So you see this. Factoring out an M1, a G, and an L, ooh, I don't want to do that just yet. What's the goal? I gotta find out what mu sub k is. Actually, I am gonna factor out an M1 just so that I can do this. M1 plus 4M1 is 5M1, so this is 5 halves M1 V squared. They cancel. M1 is unnecessary. Now I'm solving for mu sub k. 4GL minus 5 halves V squared is equal to mu sub k GL. Divide both sides by GL. And you get this. We now have everything that we need. 4 times 10 times 40 minus 5 halves 24 squared 10 times 40. Answer, hold on, oop, 5 by 400, 0.4, exact. If you see a number pop up exact like that, then you go, I got it, it's done. If you got 0.487212976218852 for something like this, you either got it right and it's fine, or it went horribly wrong. I think a valid question to ask during a test is, how nice are these numbers? Are they going to come out very nice, as in whole numbers, or simple fractions, or are they going to come out kind of messy? Vector additions are always messy. The last part of this problem, the remaining energy fraction, is EF over EI. The final kinetic energy is 1/2 M1 plus M2 V squared. The initial energy is the potential energy of the hanging mass, M2 GL. We do the same thing with the substitution. 1/2 M1 plus 4M1 V squared over M2 GL, or I'm sorry, 4M1. This makes it 5M1 V squared over 8M1 GL. 5 times 24 divided by 8 times 10 times 40. 0.0375. That's the fraction. In fact, it is. Thank you. I was wondering because that's a really small number. Oh, that makes it better. Thank you. 0.9. Which makes the number even look better. Now it's... You know that if there is friction, E initial over E final will be a number greater than 0. If there is friction, E final over E initial will be less than 0. So if you get an E final over E initial, which is greater than 0, you've got a problem. So that is problem 2. Problem 3, torque bar, standard problem. I'm looking for the tension in the string and I'm looking for M1. I give you F, and the R's, and M2. So let's draw this out. And once again, while I'm drawing this, tutors will be in the tutoring room starting at 1 o'clock and they will go until 6. All right, my two unknowns are M1 and T. So I need to pick something that will eliminate either M1 or T initially. I'm going to pick as my rotation point this one. The sums of the torques around A are equal to 0. Because it's in rotational equilibrium. Why? Because it's doing nothing. I think a valid question to ask, now granted, if it's a torque bar problem, the answer is going to be, it's not moving. It's not rotating. It's not doing anything. You have 3 forces outside of that, so they're going to be 3 torques. M1G R1 F R1 plus R3 and M2G R1 plus R2 plus R3. Torque is defined as the force times the distance from the rotation point to the force. For M1, its distance is R1. For F, its distance is R3 plus R1. For M2, it's R1, 3, and 2 together. Now we have to do the signs. All of our forces are to the right. If it's to the right and down, it's into the page, or negative. So that one and that one are negative. That force to the right is up. Thumb goes out of the page, or positive. Now, one of the reasons that, might as well mention it now. I mean, it's not really going to be on the test, but it helps explain. If you have just a simple X and Y, positive axis is up the page to the top. X is to the right, Y is up. The question is Z in or out of the page? Or positive Z? Positive Z is out of the page because when we do, this is all used in like vectors and calculus and stuff. An identity is X cross Y will give you Z, all positive. And so this is why you can say that our coordinate system that we're so familiar with is a right-handed coordinate system, because x cross y is positive z. So that's why out of the page is positive, into the page is negative. And so that's where we get the summons. We have everything but M2. Where we M1 is there. Oh, I haven't finished. It's in there. Oh, we are solving for M1. Yes. I was just okay. Physics 213, take 2. So I'm looking for M1. Oh, that makes my life easier. See, it's a good, one of the things that I really like teaching this is that I have 55 brains in the room with me that can just look over my shoulder. One of the things that I used to do, when I learned physics in high school and chemistry in high school, the classroom had 3 walls of chalkboard, and we would go to the chalkboard, half the class would, and the other half would be assigned their shotgun. And they would be a person that would just sit there and watch the problem be done. And if you do it incorrectly, the shotgun has the right to get the teacher over and have them redo the problem. I hated my shotgun. He'd just laugh at me. The good thing about it is it gets you guys to call out mistakes, because professors are going to make mistakes. But the bad thing for me is now I'm starting to rely on my students to just constantly stand over my shoulder and watch me do these things. Solve for M1. And so that is the equation. Plugging everything in. Mm-hmm.
Okay, so on my piece of paper, which I have the same problem as you, M2 equals 7 on the bottom, but on the top it says M2 equals 10.
That is probably a definite whoopsie. I'm not going to do that on your test.
Okay.
I think that when you said M2 is 10 up here, but 7 is down there, which one is it? Is a very valid question to ask during the test. And I would look at it and go, my bad. And then probably what would happen is I'd sit there and just crank out the numbers real quick and see what I got. In this case, we use 7.
Okay.
So let's just assume that we stuck with 7.
Okay.
300 times 5 minus 70 times 6. Oh yay, it didn't get a negative number. Divided by 20, and I get 54 kilograms. The other thing is this comes from another reason maybe, this comes from a fall 213 class. there are usually 3 versions of the problem. And so I think what I may have done is decided that M2 was going to be the number that I changed. And so I decided, oh, I'm just going to use 7, 10, and 13 or something like that. And one of the numbers just slipped in accidentally. Yeah, thank you. So in this particular case, we got rid of that. So 54 kilograms is M1. Now we can attack T. You solve the forces in Y is equal to 0. That is T plus F minus M1G minus M2G. M1G plus M2G minus F is equal to T. And I need more paper. That means that 54 times 10 plus 7 times 10 minus 300 is equal to 540, 240, 240 plus 70 is 310 newtons. I think that's it. And so that's test 2 from the fall. Someone reminded me by email the lecture that I posted was a repeat of some other lecture. That lecture is currently sitting on my hard drive. After this lecture, I'll post both. The other thing is there is a test 2 review already on YouTube. I want to say it is from the spring, and if it's from the spring, test 2 is around March 20th to the 27th. If it's in the fall, I would say it is around October 15th to the 20th, somewhere in there. But I think this is the one that is definitely up. One of them was definitely up because I saw it. I just can't remember which time zone it was set, or time of year it was set in. So this is going up after this. All right, good. Well, what do you want to talk about now? Yes. Number 12 on the homework. Okay. Ah, there you are. All right. So after I'm done, then the person over here, their question will answer next. So 12 is a mobile. It has multiple bars. And one of the questions that you can ask is, what's it doing? And my answer is nothing. It's perfectly balanced. It's just sitting there. So you know the triangle is the universal symbol for that's a fixed point, or that's a fulcrum. Those two are hanging, and the other thing that I know is these two are not rotating. So what I can first do is find M2. Because I know that the sum of the torques about that point is 0. M2GR3 and M3GR4. That force is to the left of the rotation point and down, or positive. That one is to the right of the rotation point and down or in or negative. So this becomes M3GR4 equals that. The G's cancel. I'm looking for M2. So it's 4 times 0.3 over 0.2 or 6. So that's the mass of mass 2. Now, one of the things that we can also do is you can change this to a force pulling down. That force pulling down is the same force pulling up because the wires remains in the same place. So the force pulling down on that bar is the same force pulling up on that bar. So the sum of the forces in Y on just that one point here is F minus M2G minus M3G. So M2G plus M3G is this. M2, 6 times 10 plus 4 times 10. So the force is 100 newtons. That's the force pulling down here. Now we have M1 on this side. We choose this as the rotation point. Since I used F here, I'll use F1 as that one. Some of the torques around that point are also 0 because it's not rotating around there. So this is F1R2, M1GR1, left, down, up, positive, right, down, in, negative. And so we get 100 R2 1, 10 R1 2, which gives me 5. Why am I not looking at the right one? Hold on. These numbers, I'm using the wrong numbers. Hold on. I'm looking at the test. Bad professor. These are right. So that's right. These are right. So that's right. Now, this one, the numbers are all messed up. So this is 100. R2 is 0.5. 10. R1 is 1. So 100 divided by 10 is 10. 10 times 0.5 is, oh, and the number, still number 5. It's just an odd quirk. Right answer done incorrectly. Yes?
Can you explain again why you chose to find M2 first?
Technically, you could go either way. Looking at this bar, actually, no, you can't go either way. Let me tell you why. I have over here several choices of picking rotation points. And I have a lot of unknowns. Over here, I don't know what M1 is, and I don't know what F is. So that's really, I got a lot of unknowns in there, and that frightens me. Over here, I can choose that as the rotation point. I know everything about the dimensions in this mass with only one unknown right here. So this is like a Sudoku puzzle, the weakest point, and you attack that point. And I'm just, can I make this brighter? Hold on. I'll figure it out later. Hold on. Exit. Menu. Where's my menu? Now I've messed this up. So this has to be the part that you do first, because it's the only part which has, like in many other equations, if we wrote the equation for this, we would have three unknowns, M1G, F, and this force pulling down on that end of the bar. Over here, this equation only has one unknown, this mass. So that's a one equation, one unknown. I attack that, and that's the reason. Question?
For number 9, can you split it up the same way down here?
Well, number 9, I would attack it, I would choose the fulcrum to be at either F1 or at F2. Because you make the distance 0, then you could ignore, if I chose the fulcrum under F1 as the rotation point, then I could ignore F1 in the construction of the equation.
Yes. So with the M2, M3, and 12, do you just add those together and act like one big mass? Would you like rotate around that to define M1?
Which one are we talking about?
12.
12? What I did is I took M2 and M3, added them together to get a force with F1. And then I hung effectively in F1 at distance R2. I simplified. Your question. I'm going to do 7 and 9 when I'm done with 12. What was, there was another question about what problem are we going to do after this one? I got 7 and 9 on the list. I thought you were asking.
Yeah, I was going to ask like the way you tackle like the rotation problem with the disc, like the first step you had like a 3-step method. I'm just kind of confused of where to start with some of them.
Okay. Well, I'll deal with that after 7 and 9, which will be after 12. Okay. So to finish 12, we have to figure out what F is. That just sums the forces in Y. Yeah. So many buttons I have to press. All right, so 7, we're gonna finish 12, and then do 7, 9, and then some rotation stuff. A what? 2 on it? All right. Okay, all right. This is what we're gonna do. We're gonna do 12, then 9, then 7, then 2. And then after all that, then I'll take more requests. All right. Uh-huh.
You said we're looking for F now. I thought we found it. Wasn't that 100?
What we did, that's F1.
Okay.
That F1, I initially labeled it as F. That F1 is this force pulling down on that bar, or that force pulling up on this bar.
Okay, so we're looking for
This is, yeah, this, I originally labeled it as F, but I've forgotten that I had used F initially as the force of the fulcrum.
Okay.
All right.
Can we put the other page up there? Sorry, last thing.
All right. So you want to see 12?
No, like the page that you were working.
Oh, the previous page. Okay. So the vertical forces, there are 3 of them. 1, F, the fulcrum on the bar, the normal force from the fulcrum on the bar. 2, M1G, the force pulling down on the left. And then F1, the force pulling down on the right. So this gives me M1G plus F1 is equal to F. M1 is 5. F1 is 100, so that means F is 150 newtons. And so that is it. Now, we will now begin with the next problem, number 9. Now, number 9 has 2 forces pushing up on the bar. It has 3 masses pulling down. So what we need to do is we need to choose a rotation point. We'll choose it at F1. So we can eliminate the torque at that point from F1. The sum of the torques at alpha is 0. It's in rotational equilibrium. You get a torque bar, that thing is in rotational equilibrium. Now, that is M1G, M2G. Oh, I'm going to need distances. Hold on. M1GR1, M2GR2, FR2 plus R3, and M3GR1 plus R2 plus R3. So there are 4 torques. M1G, distance R1 to there. M2G, distance R2. F2 is the distance R2 plus R3, there to there. M3G is R, and I messed that one up, R2, 3, and 4. So the distance from there to there is R2, 3, and 4. Now we got to figure out signs. Everything is in relationship to A. M1G, left, down, out of the page are positive. M2 and M3 are both right and down into the page. So M2GR2 and this last term are both negative. F2 is to the right, but up, thumb out of the page or positive. And you get this. Now solve for F2. M2GR2 plus M3GR2 plus R3 plus R4 minus M1GR1 equals F2 R2 plus R3. Now factor out a G off the top, M2R2 plus M3 R2, 3, and 4 minus M1R1 close divided by R2 plus R3. And we get that. Now we may plug and chug. 10, M2 10, R2 0.1, M3 5, R2 0.1, 0.2, 0.3 minus 3, 0.4 all over 0.1, 0.2. That gives us .33 repeat. And that's F1. F2, we know that the sum of the forces in Y is equal to 0. That gives you F1 plus F2 minus M1G minus M2G minus M3G. We're looking for we got F2, now we'll get F1. So M1G plus this, plus that, is this, 3 times 10 plus 10 times 10 plus 5 times 10 minus F2, 93.33 repeating, gives us .8667 or 66 repeating. And so that's the answer. I would accept 93.3 and 86.7. And so that is 9. Okay. Number 7, like number 8, are a little bit different in the sense that I wouldn't call them rotation where alpha is 0 or alpha is non-zero. I would call these conservation of angular momentum problems. When you with alpha equals 0 problems or alpha not equal to 0 problems, the geometry, the mass distribution is constant. In 7 and 8, the mass distribution or the geometry actually changes. So the only thing that you have to remember is when the geometry changes, it screams conservation of angular momentum. Something like this, I'm pretty focused right now on alpha equaling 0 or non-zero for the test. So conservation of angular momentum other than multiple choice, most likely will not be on the test, but very much could be on the final. For number 7, this is like the childhood, the playground problem. The moments of inertia change. Initially, the moment of inertia is the moment of inertia of the disk plus 4 times the moment of inertia of the point particles. This gives you 1/2 mass of the disk r squared plus 4 mass of the point r squared. That would be the initial moment of inertia. The final moment of inertia is still the moment of inertia of the disk, but the new moment of inertia of the point particles times 4. The point particle moment of inertia does change. So this becomes 1/2 mdr squared plus 4 mass of the particle. Since I'm using caps, I'll keep using it. Of that. Let's just get numerical values. 1/2 80 2 squared plus 4 30 times 2 squared. So this is 640 kilograms meters squared exact. This is 1/2 80 2 squared plus 4 30 0.5 squared. $190. What we do is conservation of angular momentum is L is equal to L prime, or L initial is equal to L final. L, which is I omega equals I prime omega prime. The new angular velocity is just the old moment of inertia times the initial angular velocity divided by the final moment of inertia. This gives you 640 times 2 divided by 190. And that gives me a not nice number of 6.74 radians per second. Let me see if there is a nice number inside. Nope, no nice number. So that's omega. We have to get f prime and period prime. 2 pi f prime is equal to omega prime. So f prime is omega prime over 2 pi, which is 6.74 divided by 2 pi. Ooh, the number may be coming in there. Nah, it's still nasty. 1.07 hertz. And since period is the inverse of frequency, the period is 0.93 seconds. And so that's number 7. Okay, last one on the list, number 2. Number 2 is similar to the problem on the test that we worked on today, because it has the highly suspect time of time equaling 100 times the square root of pi. Just begs for attention. Now, one of the questions that you've asked is, how do you do these rotation problems? What is your motivation behind doing it? I do find it a tad, well, let's just look at it. I have the number of rotations. I have the mass of the disk. I have the radius of the disk. I have the time, the highly suspect or suspicious 100 times the square root of pi. I'm told that the omega naught is 0. The moment I see omega naught is 0, this thing is screaming alpha is non-zero. Because if omega naught was 0 and it's not accelerating, it's not spinning up, then we just have a disk that's sitting there doing nothing. It's a boring problem, so it's got to spin up. So alpha is definitely non-zero. I'm looking for alpha, and I'm looking for the mass of the stick. Mass of the disk. I've got the force, 300. So for something like this, the two equations that I would initially start with are theta equals theta naught plus omega naught t plus 1/2 alpha t squared. The other one would be that the sum of the torques is equaling to I alpha. If you look at this thing and you know that it has a non-zero alpha, I throw those equations out right away. If it was a zero, sort of like a Fisher-Fury problem, I would write this one, but not that one. But it's definitely a non-zero alpha. I know that 2 pi n is equal to theta, so I can rewrite this as 2 pi n equals 1/2 alpha t squared. In this particular case, I'm looking for alpha. I know n and I know t. At this particular case, I would attack alpha right now and solve for it, get a numerical answer. Because A, I'm looking for it. If I wasn't looking for alpha, I would continue with the alphabet soup mode in this. This gives me 4 pi n over t squared equals alpha. So 4 pi n, 300, t squared is 100 squared pi. And that gives me and I need someone maybe to double check this math. Well, no, I don't need anybody to check this math because it comes out 0.12 exact. And that's alpha. If you do the plug and chug method, because you guys are constantly rounding, you're never going to get the precise answers. The way that I make these problems are so that the alphabet soup style rewards you with just solid whole numbers that don't go on forever. The next part, the mass of the stick, I've got to use this. Now, there's only one force, so there's only one torque. So Fr. The moment of inertia of the system is the moment of inertia of the disk plus the moment of inertia of the stick. Fortunately, it's rotating about both center of mass center of mass of the stick and the disc. So I have alpha. I'm looking for the mass of the stick, so what I'm going to do is Fr equals moment of the that. I'm distributing alpha. To get it to this. Now, since I did not specifically ask for the moment of inertia of the stick, I'm going to substitute in what those moments of inertia are, which will be given to you on the test. Because the stick runs directly across the disc, this problem, just to show the evolution of a problem, the circle on the left and the circle on the right are identical problems in the sense that the bar is welded directly across. The big difference is I made it way more noticeable because a lot of people were not quite clear as to where the stick was. So I'm looking for mass of the stick. I know that L is 2R. So this is Fr minus 1/2 mdr squared alpha over alpha 1/12 ms 4r squared. Solve for ms. So 12 over 4r squared. I'm going to start poking stuff out. R F minus 1/2 mdr alpha over alpha is equal to ms. Now, one of these r's cancels with that r, and simplify it, I end up with 3 over r f minus 1/2 mdr alpha divided by alpha. And all of that is equal to ms. One of the things that you could sit here and do right now, and even I'm looking at the equation, and ask myself, do I have true confidence in this equation? Is it formed correctly? Right now I'm thinking, I have no idea. Let's find out. Let's do a unit check. 3 over r, that's 1 over a meter. A force is a kilogram meter per second per second. Mass, kilograms. That's m, or meter for radius. Alpha is inverse second squared. All of this over 1 over second squared. This minus this will give you something of the same units. Kilograms, meters, second squared. Over 1 over second squared. That will cancel out with that. 1 over meters, kilogram meter. The units do check. Yes?
Since you canceled out the R's, why would the alphas not
Because if it was F alpha minus MDR alpha over alpha, I could factor out an alpha. But because there's no alpha term there, I can't factor it out. I can't pull an alpha out. If I can't pull an alpha out of here, I don't have an alpha to cancel out with that. Like this, there was an R in there, which made me pull that out. But since there was no alpha there, I couldn't. Now we plug everything in. 3. I get so used to doing this, I lose track. R in this case is 2. F in this case is 300, 300 newtons. Coincidentally, it's the same number of rotations. Minus 1/2 mass of the disk, 1200. R is 2. Alpha is 0.12. All divided by alpha, which is 0.12. So that cancels with that 2. I'm left with 300 minus 1200 times 0.12 divided by 0.12 times 1.5, and I get an answer of 1950 exact kilograms. This was a test question. This was, I don't remember when I did this, but it was a test question where I had the numbers work out excellently. So that's what I plan on doing this afternoon, is writing test questions that will turn out well. Yes?
I'm still confused on how to know, like, if alpha is 0 or not 0.
If is it spinning, if it starts at rest, like that calculator is right now, if it's starting from rest, it has to have a non-zero alpha. If it's just rotating and rotating and rotating, and you just,
It's like I get that, but whenever I look at a problem and I'm given the velocity is like 10,
yeah.
I don't really understand how to understand alpha.
Typically the ones that give it away are, if you see a symbol like that, that's an alpha is non-zero problem. Definitely if you see this, if you ask the question, I think a valuable question that you could ask during the test is, what's the initial angular velocity of this disk? If I say non-zero and that force is missing, you're dealing with an alpha equals 0. Probably the thing that screams out, so for this one, alpha is definitely non-zero. How can you tell? It's a disk with a force. Disks with force means you got a torque. That torque implies that alpha is non-zero. In this one, it specifically says that the fish's speed is constant. If the fish's speed is constant, that's 0. And since V is equal to omega R, if the speed is constant, its dv dt is 0. And V is omega R, so dv dt is r d omega dt. If anybody takes calculus 1, this is basically what I did is I just took a derivative. Cover your ears if you've never taken that course. So if dv dt is 0, d omega dt has to be 0. Therefore, d omega dt is alpha, so alpha is equal to 0. So if you see that, you also see it in multiple choice problems. Thread is coming off a spool. The thread is coming off at a constant rate. That constant rate is screaming at you, alpha is 0. If I said it's coming off at a non-constant rate, if it's accelerating, then you know you have an alpha that's non-zero. Woo. So for I would say that if the alpha is non-zero, the setup of the problem is easy. You first attack it with that. If alpha is 0, you still attack it with that. But then there are a whole bunch of other weapons that you have to deal with. V is omega r, AR is V squared over R, 2 pi F is omega. There's a whole bunch of other things that you have to deal with. Yes?
Could you briefly explain the parallel axis theorem? I think you said earlier that it would be.
Okay, yeah. Yes, yes, yes. So, parallel axis theorem is used when the rotating object is not rotating at its center of mass, and you need to know its moment of inertia. Oh, that's a lot of writing. I don't normally write that long, unless it's very important. So the parallel axis theorem is used in situations where the rotating object is not rotating at its center of mass. All of our center of masses for all of our objects, the disk, the stick, are all going to be at the dead center of the object. So it is not used when the stick is rotating or the disk is rotating about its center of mass. So if it's rotating if it is rotating about its center of mass, the moments of inertia are easy. I have them written down for you. And it's just this. But in situations where the object isn't rotating around its center of mass, then it just adds an extra layer. So in situations like those, where you're not exactly rotating about its center of mass, you use the parallel axis theorem. That the moment of inertia that we use, its new moment of inertia for these guys, is its center of mass moment of inertia plus its mass times d squared. So for a stick, you use 1/12 ml squared. For a disc, you use 1/2 mr squared. Now, that's the mass, and d is the distance from rotation point to center of mass. So in these cases on the right, that distance, hold on. This distance there is your d. And for that particular case, the distance is L/2. Because in that particular case, it's rotating about its endpoint. Here, that is its d, and it's whatever value I give you. If I say, if the stick was 0.8 meters long, its center of mass is at 0.4, and I say it's rotating at 0.6, the d that you use is the difference, the distance, or 0.2 is equal to its d. In these cases, that is your d, and d in this case is equal to r. Here it is just whatever I said that distance is, and so it could be anything. So in the case of this stick, the new moment of inertia would be 1/12. Let's say the mass of the stick is 10 kilograms. This moment of inertia would be 1/12 times 10 times L squared, 0.8 squared, plus its mass, 10, times d squared, 0.2 squared. And so adding all of that up, .93 repeat kilograms meters squared. So it's just adding that extra bit, that extra md squared, and then it tests your knowledge as to what is that value d. It's a fairly simple concept. It looks, there's a whole parallel axis theorem. That must sound so complex. No, it's not. It's really easy. You just go, well, what's d? And then you tack that on with an m. Yes?
Can you always give us center of mass is?
Will I ask the question? Will I always give center of mass?
That's the measurement for center of mass.
In the two types of objects, the stick, center of mass will always be dead center in the stick. So it's always half. In terms of the disc, it's at the center. So then it's radius r. So it's nothing crazy is going to go on with those things. If I say, the length of this stick is 0.8, and I rotate around its end, what is the value of D? 0.4. Because the center of mass is there, so 0, 0.4, 0.8. So the distance D, there to there, is 0.4. If I said it was a disk, and I decided to rotate, let's say R was 2, and I made it rotate around that point there, where that distance was 0.5. So that distance there was 0.5. What is the distance D? 1.5. So if that distance is 0.5, that distance is 1.5, and the distance from there to the rotation point is 1.5. So it's being able to identify what D is. Most likely, I'll probably do a parallel axis. It'll be a contribution to the moments of inertia. I can't make it look too complex, otherwise the math will get crazy. And I typically do like 2 or 3 of these rotation problems, and then I pick the one that makes me go, I think they can do that. There's some that make me, I'll look at it and go, oh, they can't do this. So I tend to make it a little bit more gentle. The one thing that is interesting, if you look at the parallel axis theorem for let's say you have a point mass moving around radius r. Well, if you look at the parallel axis theorem, the moment of inertia of the center of mass of a point particle is 0. So you're just left with m, and then the distance from the center of mass to its rotation point is r. So that's why the moment of inertia of a point particle is mr squared. Mr squared is a point particle having the parallel axis theorem applied to it. You're already using it for a point particle. If I will keep the geometry simple. I think in something like this, there will only be one object, or either a stick or a disk, where it is off-center and you have to use parallel axis theorem. I'm not sure how I would use it. It depends on how confident I am in you guys. And for the homework, I may keep it simple. What I'm thinking about for the parallel axis theorem is maybe not necessarily a problem, but more like give you that sketch and say, what is the value of D? Stuff like that. Having you being able to identify it. Yes?
Can you put the sheet up that showed the stuff about alpha? The equal to 0 and not equal to 0.
For the alpha equals 0, I would look at when I did the equivalent of the Fisher-Fury problem. All that stuff. And then, though right now I'm having, well, this just shows what's going on in my head. I'm having way too much fun figuring out those geometries for new moments of inertia if you put a stick and a circle together. So probably problems like this one and that one. Also, I will admit that in both cases, I did not use the parallel axis theorem in it. So that's why I'm leaning towards, and also this is Dr. Eschenberg's great weakness. The lecture before the test, he's basically testing various problems and seeing how it goes. So Dr. Eschenberg is leaning towards in rotation problems where the parallel axis theorem is not used. But parallel axis theorem could be used in the multiple choice. Now, and the response from you guys is, oh, I could do that. Yeah, that's fine. So that's what I'm leaning towards. That's what I think is going to happen. I can't tell you what's going to happen, but that's what I'm leaning towards. Any other questions? Okay. Homework due at 6. Tutors are here from 1 to 6. I've got office hours 2 to 4-ish. I'll see you guys tomorrow at 10. These lectures will be up